Welcome back. In last several lectures, we have discussed and studied on helium ion microscope. Today, we will I will be talking on some additional topic on helium ion microscope or ion microscope. Those are scanning transmission ion microscopy and microanalysis with helium ion microscope. In particular, we will be discussing on imaging with transmitted ions and also composition measurements with helium ion microscope. So, these two things we will be discussing today, that is, these are some additional capabilities of helium ion microscope. First, let us talk about scanning transmission ion microscopy. So, as the name suggests, scanning means the ion beam has to scan on the specimen, and transmission means the ion should transmit through the sample, and it has to pass through the sample, and then image that will form is nothing but transmission image. So, what has to be transmit, or that is the ions has to transmit through the sample. Similar to scanning transmission ion microscopy, we have scanning transmission electron microscopy. When electron beam pass through the sample, that is called transmission electron microscopy, and when electron beam scans across the sample, we say it is a scanning transmission electron microscopy. Both are similar type. So, here if the sample if the electrons or ion has to transmit through the sample, then first thing is that the sample should be very thin. If it is not thin, this electron beam or ion beam cannot pass through it. Second thing, we should have a certain device or adapter to be placed so that at the bottom we have some kind of screen or a type of detector to collect how much ions or electrons are transmitted through the specimen. So, that has to be done. So, it is little bit similar to the transmission electron microscope study or TEM, which we are not covering here. The sample preparation is done in the similar manner as that of prepared for the transmission electron microscope. We normally take a copper grid here, it is a copper grid, and the copper grid has a coating of very thin layer of carbon, around approximately 5 nanometer thick carbon, transparent carbon, or some kind of polymer formbar type of coating to be provided that act as a support. Now, on this grid, which has a very transparent thin layer of carbon, on which we will place our sample, and that has to be put under the electron beam or ion beam. So, then as it is very thin, almost all ions will pass through it, except where sample is placed. If the sample is placed here, if sample is thin enough, then some ions will pass through it. If sample is thick enough, then ions or electron will not pass through it. So, from the transmitted ions, we can get the signal. So, for example, here a sample is placed which is thin enough, so that some of the ion will pass through it, and those ions will come and strike at the bottom. We have a object which is tilted at 45 degree, and ions will come and strike. This is gold coated. Once a ion strike to the gold coated surface which is tilted at 45 degree, that would create some secondary electron, and those secondary electrons will be detected by a normal Everett Thornley detector. Then we will see from which region how many ions pass through it and how many electrons are generated, secondary electrons generated or signal generated, and then we create an image. This is what nothing but transmission microscopic image. If the incident probe is ions, we say it is a ion microscope. If it is electrons, we say scanning transmission electron microscope, and here our electron beam or ion beam is scanning over the specimen, and then collecting the transmitted ions, and from the transmitted ions the signal generated are used for imaging purpose. This is what the scanning transmission ion microscopic image, and because the ions which are passing through the sample, they can produce one ions can produce more number of secondary electrons, like 3 to 8 number of secondary electrons. Therefore, signal to noise ratio is quite good. Moreover, again the ion induced secondary electrons have a better contrast as compared to the electrons. So, in that respect, scanning transmission ion microscope is superior compared to the scanning transmission electron microscope. But on the other hand, ions have a much larger size and heavier mass. So, we cannot easily make the ions to pass through the specimen unless and until the specimen is very thin enough. So, this is a disadvantage of using scanning transmission ion microscopy. To make the sample to be very thin is not that easy task, and therefore, most of the ions cannot pass through it. So, therefore, actually in practicality, scanning transmission ion microscopy is not that much popular or have been used in the scientific community yet. Mostly scanning transmission electron microscopy attached with TEM is extensively used for microanalysis and also other purpose, because in transmission electron microscope the incident energy is much higher, in the order of around 200 kV to 300 kV. Therefore, they can easily penetrate through the sample and provides the information which we cannot get it by scanning transmission ion microscopy. So, here you see a type of device that is being used here. So, incident ions comes, and here we put that means hold the grid with the specimen. Here is sample on the TEM grid. Then transmitted ions which comes is get collected. Transmitted ion strikes to the gold coated surface, and then the secondary electrons generated is used for the imaging purpose. And here you see the a specimen like magnesium oxide cube type of structure in a scanning transmission ion microscope. Here the periodic dark and bright contrast tells about the thickness fringe in the left side of image, and in the right side of image the contrast here, dark contrast, indicate dislocation inside the specimen or inside the sample. So, some of these information like presence of dislocation inside the specimen cannot be studied by the scanning ion microscope when we study 3-dimensional feature. Here you see the information which is inside the specimen, that is the inside the specimen or microstructure, because the image is formed from the ions which is passed through the specimen. On the other hand, in our just normal scanning ion microscopy or scanning electron microscopy, we were just seeing the surface features, the topology, surface features from the signals collected from the specimen. So, this is about scanning transmission ion microscopy. As it is not as popular and not extensively used, I am not covering much detail on it. We will go next to another important topic, microanalysis with helium ion microscope. Microanalysis means measuring the elemental composition of the specimen. It is very important. So, for all scanning electron microscopic technique, most of the cases energy dispersive detector is attached, and that is used for measuring the elemental composition of the specimen. Because any operator or user would like to know what material he is studying under the microscope, whether it is a gold or it is just a iron or anything. So, it is therefore important to know the elemental composition that is of the specimen which is under observation. In SEM, we know we use energy dispersive analysis, where every atom have a nucleus at the center, and then we have electrons, and when incident beam strikes on the atom, then it will first knock out an electron, inert shell electrons. It will knock out an inert shell electrons if the incident electrons have energy greater than ionization potential of that particular electron. Once a vacancy is created here, then another electron from the outer orbital jump back to this vacancy, and thereby this energy is caused as a X-rays. So, by measuring the energy of this X-ray, we know what atom is it, and also by knowing how much such X-rays is coming, we can quantify the atoms present or element present in our specimen. So, in these cases, to create or to remove knock out an electron from the inner shell, the incident electron's energy should be greater than the ionization potential. So, similarly, in case of whether it is same, it will be same for ions, actually not. Even though energy of the incident ion is equal to or greater than ionization potential of an electrons of an atom, it cannot still knock out an electrons, because the ions though have energy much higher, they have a much lower velocity. Once they penetrate the sample, they have a much lower velocity, and the velocity of the ions cannot match with the velocity of the orbiting electrons. As they cannot match the velocity of the orbiting electrons, they cannot initiate the ionization inside the material, and thereby the energy of the incident electrons just greater than the ionization potential or little greater than ionization potential is not sufficient enough to produce the X-rays from the specimen. For example, let us say we have here let us say it is let us say chromium. For chromium case, to produce a KSL X-rays, if the incident electron energy is around let us say 7 keV incident electron energy, it can produce chromium K alpha, which has an energy of around 5.5 keV. So, here incident energy is higher, so it can certainly produce 5.5 keV, but for the ions, for helium ion, in order to produce this chromium K alpha, this energy should be 40 mega electron volt, 40 mega electron volts. You see, there is such a huge energy we need to create an X-rays from chromium K alpha 5.5 electron volts. Therefore, practically it is not possible, not feasible, because our helium ion microscope operated in the range of 25 to 35 keV. So, with that energy range, our helium ion microscope operate, unless and until we go to very extreme, we cannot do it. So, it is not it is not a possible way to measure the X-rays from the specimen to measure the composition. We need to have some opposite other ways. So, one of the approach is to use backscattered ion, that is called Rutherford backscattered ions. So, we know that many of the ions backscattered, helium ions backscattered after the incident on the specimen, strikes the specimen. So, many backscattered ions that are generated, we can measure the energy of the backscattered ions to tell which atom present in the specimen. For a given ion type, the energy of incident and energy of the backscattered ions have a certain relation. As a function of atomic mass, it changes. Here you see how they changes, like energy of the backscattered ions, and here is the target atomic weight. We see it is not very linear, but at a particular takeoff angle of incident ions and the detector placed at a particular incident angle, let us say it is 90 degree angle at 90 degree angle between the incident ion and the detector, the relation of E scattered, that means energy of the scattered ion, backscattered ion, E scattered to the incident energy ion E0, can have a relation like M2 minus M1 divided by M2 plus M1. Here E scattered is the energy of the scattered ions, E0 is the energy of the incident ion, and M1 is the mass of the incident ion, mass of incident ion, which we know m2 is the mass of the target atom, that is our specimen target atom. We know m1, we know E scattering, energy of the scattered ions, we know incident energy. So, we can know from there we can calculate the mass of the target atom, and it is possible to an extent to knowing the mass of the target atom from the backscattered backscattered ions. And if we look at 90° takeoff angle, which is most optimum, lower atomic number has some kind of linear relationship. But as we increase the atomic weight of the specimen, these are placed much closer at energy. Our detector is not efficient enough to differentiate these energy, so that we can able to tell the difference between, let us say, iron, chromium and other materials here. So, first problem. So, this is the problem. In the lower atomic number, to an extent, so we can able to distinguish, but at higher atomic number we cannot distinguish. And second point is the thickness. As thickness of the material changes, the energy of the backscattered ions will also changes to an extent. So, for example, the detection of the backscattered ions also depends on the thickness of the specimen, as well as the composition and the beam energy. So, all these factors it depends. As the thickness is increased, the mean energy of the elemental peak decreases in magnitude. As you see, as the thickness is increasing, the beam that means the mean energy of the elemental peak decreases in magnitude. And second thing is happening what? As the thickness is increasing, these individual peaks are getting broader. For example, this is 30 nanometer thick sample. So, once ion beam penetrate into a thicker sample, they keep on interacting with the specimen and losing its energy, and the backscattered ions which come out the specimen, they automatically lose their energy to a great extent, and therefore, the mean energy is decreasing with increasing in the thickness. And second thing, they become broad. Once it become broad, it will be not easily be distinguishable and quantification cannot be done. So, this is again not a suitable technique. RBI's technique, Rutherford backward scattering, will therefore be least useful on samples which are thick or contain high atomic number materials, and when beam energy is low. This problem is again there for for ion microscopy to analyze the composition. But there is one alternative to this, that is called SIMS, secondary ion mass spectroscopy. So, in the secondary ion mass spectroscopy, an energetic beam of ions, as the name suggests, secondary ion mass spectroscopy, we measure the mass of the secondary ion, mass to charge ratio of the secondary ions, and therefore able to tell what element present on the specimen. So, an energetic beam of ion, it is called primary ions, is used to sputter the sample. So, primary ions will go and strikes on the specimen and take out the secondary ions. So, it will bombard on the specimen surface and knock up the surface atom, that is called sputtered atoms, and by measuring the mass to charge ratio of this sputtered atom, we will able to tell what atom is present on this specimen surface. So, the primary ion penetrate the target, lose all or a part of energy during the collision cascade with the target, and this process will lead to ejection of one or several target atoms, that is the sputtered atoms. Among the emitted particles, there will be ions, that is called secondary ions, and these secondary ions, when we measure the mass, that is of our interest in the secondary ion mass spectroscopy. There is dedicated SIMS, secondary ion mass spectroscopy, to measure the composition of everything from hydrogen to all the element in the periodic table. This is capable of doing all element in the periodic table. There is no other technique, so it can measure the composition of hydrogen in a solid sample. These ions are extracted, the secondary ions are extracted using an electric field and accelerated to the mass spectrophotometer, and mass filtered and counted by the detectors, and it produces it will allow us to know the elemental composition of the surface, because it is important to note that atoms are mainly spotted from the first top few layers. So, it is a type of surface analysis technique which will tell about the composition of the surface. Now, you see a problem with helium ion microscope for using the SIMS. For all ion except helium, the spotter yield increases with increasing the impact energy. Certainly, impact energy increases means the spotted yield will be more. Spotted yield means the secondary ions will be yield more, but for the helium it is opposite. When we increase the impact energy, yield is not more. Then what happens? Why not it is more? It is because helium ions have a smaller mass, and they will, with increasing the energy, they will penetrate more deeper. Their beam range is deeper. Once helium ions goes deeper into the specimen, they cannot easily come out of the specimen, and once they go deeper, certainly they are lost inside the depth of the specimen, and they would not be efficiently able to collect, efficiently able to spot out the atoms present on this specimen surface. This is the problem with helium ion microscope. On the other hand, other ions which is a heavier mass, they bombard with a larger mass, with a larger momentum, therefore could spot away a more number of specimen when they come with higher energy. And therefore, helium ions used in helium ion microscope able to provide high resolution image, no doubt, because they have a smaller interaction volume. From very near the surface signal comes out, but is only capable of spotting most element and materials at the rate which is too low to be practically meaningful for microanalysis problem. So, our helium ion microscope should have another source with a heavy atoms, heavy ions such as helium and neon. So, neon can be incorporated to helium ion microscope to make this composition analysis practically possible. For the composition analysis, therefore, our helium ion microscope should be attached with a neon or heavy ion source. Two important things is there are two important things in the measurements of composition. One is the secondary ion current, and another is useful yield. These two are important when we discuss about the sensitivity. Actually, sensitivity of these seems is very good up to parts per billion level, and for helium ion the useful yield is generally low. Useful yield is nothing but the ratio of the spotted ion, ratio of spotted ions to then spotted ion detected to the spotted atom. This is the useful yield, and this useful yield is generally lower with a helium ion microscope or with a helium ions. In order to maximize the ionization potential, and that is the secondary ions, we need to use some reactive primary ion species. The reactive primary ion species would do certain reaction with the surface and will allow to produce more secondary ions, and in particular to enhance the emission of the negative secondary ions, electropositive primary ions species such as cesium is prepared. Opposite case, if we want to if we use electronegative primary ions such as let us say oxygen radical, that will favors for the emission of positive secondary ions. For example, let us say aluminum, indium, such kind of positive secondary ions we want to study in our specimen, then we should bombard it with a electronegative primary ions. In this way, we can increase the useful yield, and therefore, the composition capability of the equipments or SIMS. It is a SIMS machine. How it is done? It is in the certainly in the ion microscopy column. We have additional things here which is retractable ion optics, which is placed below the column, and that would allow us to collect the ions, secondary ions, and that secondary ions will go secondary beams of axis by passing through the transfer lens, etc. It will go to a mass spectrometer. So, there are many kind of mass spectrometer such as quadruple mass spectrometer. We have time of flight mass spectrometer, and we have magnetic sector mass spectrometer. For example, quadruple mass spectrometer have not very high mass resolution and low transmission, and it cannot do parallel measurements, or scanning it cannot do the scanning. Similarly, time of flight have a good wide range of the mass measurements can be done in case of time of flight mass spectrophotometer, and that would produce quite a high that would allow us to measure the molecular ions with a larger mass, but again that cannot do the scanning and simultaneous measurements of different ions is also difficult. On the other hand, magnetic sector mass spectrometer allows to do parallel or simultaneous measurements by using several detectors. One is a fixed detector and another is a movable detectors. With this kind of detectors, we can do the simultaneous measurements of different species present on the specimen and know their composition. So, design requirements for the SIMS, the size and weight of this certainly size and weight of this spectrometer should be compatible for mounting in the helium ion microscope. The extraction system should not significantly degrade the probe size, because extraction system means we have to apply potential to collect or to extract the secondary ions, and that potential can influence the spot size, primary beam spot size, because this is very fine primary spot size. So, it should not affect, it should not significantly degrade, otherwise it will deteriorate the performance for the imaging. Detection of the positive and negative secondary ions should be possible. It should allow us to not only detect positive not only detect one type of ions, but both type of ions simultaneously. As the secondary ion current is normally low, extraction efficiency and overall transmission of the spectrometer should be high. Parallel detection of the secondary ions is important for avoiding the poor sample consumption in the duty cycle. That is why we use we use magnetic sector mass spectrometer in the SIMS attached to the helium ion microscope. Similarly, acquisition time of the SIMS image should be similar to that of a secondary electron image, and reactive gas prodding is integrated to the SIMS to improve the useful yield. So, reactive gas prodding such as cesium and oxygen radical ions is important. This is a mass spectrum. What you can see here in this mass spectrometer, mass spectrum, it has a very that means unique tool to not only detect presence of hydrogen, but also the isotopes, like as you see here lithium 6 and lithium 7. Similarly, we can see the boron 11 and boron 10. So, not only it can allow us to detect hydrogen, but also it allows us to detect the isotope with a very high sensitivity. This is a mass spectrum for lithium titanate and boron nitrate nanoparticles mixture on a silicon substrates with a neon ion beam with an acceleration voltage 25 keV at 6 picoampere current. So, they have a quite good mass resolution. Quite a wide range of mass can be also detected. In case of SIMS with helium ion microscope, where we use magnetic sector mass spectrometer, we can only detect monoatomic or small clusters, not large molecular clusters can be detected in this process. For that kind of study, one should use time of flight spectrometer. The matrix element which is important here, matrix element matrix effect means the overall sample effect. It is that overall sample have a strong, there is a strong dependence on the ionization potential of the secondary ions to the local sample composition. It is very important effect, and this matrix elements complicate the quantification of the same signal. So, this is the formula for measuring the composition of unknown materials. Let us say is the concentration of this species. We need to know the secondary ion current of the same species, useful yield, IP is the primary ion current, and Y is the sputtering yield. So, knowing this, one could able to know these are all can be measured. One can measure the concentration of the species. Alternatively, one can get the relative sensitivity factor, RSF relative sensitivity factor, where IEX is the intensity of the secondary ion of trace element that we want to analyze, and IM is the intensity of the matrix, and the relative sensitivity factor needs to be determined by analyzing the sample of a composition that is known or similar to the sample composition. So, by knowing this, doing a standard sample, and then from this intensity 2 we can measure the composition of unknown material in a SIMS. We can do other study with a SIMS also. In addition to the mass spectra measurement, mass spectra gives us the composition. Mass spectra gives us the composition of the specimen. We can do the depth profiling. Depth profiling means we can sputter away layer by layer, because it is a surface analysis technique. We sputter the surface and then measure the mass of these ions, secondary ions. Similarly, we can keep on sputtering at every level. We can measure the mass of the sputtered atoms, sputtered ions, particularly sputtered ions, and then at every depth what is the composition of the sample can be measured. That is a depth profiling, and from that depth profiling we can particularly analyze multi-layer thin films composition at different layers, what are their composition, at the interface what is their composition, these things can be measured. We can do 2D imaging. 2D imaging, as you see here, this is a 2D imaging of a sample lithium titanate boron nitrate nanoparticle. The mapping of or distribution of the lithium 7 isotope and boron 11 isotopes, how they are distributed in this sample is measured by using SIMS with a primary beam of 27 keV, kilo electron volt, with a neon with 6 picoampere current. So, this is a 2D imaging. We can do the 3D imaging, 3D mapping of this specimen by using the SIMS technique. These all can be done using a SIMS, secondary ion mass spectroscopy. So, in conclusion, what we have seen that scanning transmission ion microscope can be used for very thin films. That means, one has to make the sample to be thin to be studied by scanning transmission ion microscope. Actually, practically we do little with such kind of study in a helium ion microscope, because scanning transmission electron microscope give much better performance, because electrons have a much higher energy and smaller size. They can penetrate much easily into the specimen. We do not need edge thin sample edge that we need in helium ion microscope. And for composition analysis in a helium ion microscope, the SIMS is the best alternative useful that available today. It is very sensitive. Its sensitivity is down to parts per billion level for elemental and chemical analysis that can be done with a helium ion microscope. Another important thing is that in the resolution of helium ion microscope is ultimate surface resolution down to 0.5 nanometer. But helium ion is not suitable or not capable enough to sputter away the surface atoms, and therefore, the useful yield particularly is very low, and thus helium ions is not enough for microanalysis or composition analysis. For that, one has to attach other heavy ions such as neon or argon, some other ions such as gallium also can be used. This is important for microanalysis technique for measuring the elemental composition or chemical analysis to a interaction volume of 10 nanometer. These are the reference, the same books. Thank you.